Hello everyone. In today's video, what we're going to do is learn how to implement a quantum half adder using Q sharp and also learn how to call operations within Q sharp. Now, even before we talk about the quantum half adder, let's look at what a classical half adder is. Uh, as you see above my head, the classical half adder is basically a very simple circuit that can give me the result of the addition of two classical bits or two bits, right? So I have the two bits A and B here, and my result will be the sum bit and the carry bit. For example, if I had the bit values as A is equal to 1 and B is equal to 0, the sum I should get as 1 plus 0, which is equal to 1, and the carry will just be 0 because there is no addition carry when 1 plus 0 is added. Now, if I had something like 1 plus 1, my sum would be 0 and my carry should be 1. Now, let us look at the circuit, how the half adder is implemented. So, for the sum part, we have an XOR gate. And for the AND part, we have for the carry part, we have an AND gate. So let's say again 0 and 1 was my input. So 0 XOR 1 would give me 1, which is the sum. And my 0 and 1 would give me 0, which is the carry part. Now I have implemented the same logic here in Python. So what I'm doing here is I'm taking in two classical bits and I'm returning the result of the half adder. So A and B will return me the carry part and A XOR B will return me the sum part. So let me just run it. So as you can see here, we have the half adder implemented in Python. But now let's look at how to implement the same thing using a Q sharp program. So this is the half adder.qsharp file where we're going to implement our quantum half adder. But before we get coding, let me show you the quantum half adder circuit. So that's above my head right here. So it's very similar to the classical half adder, as in we have 4 qubits here, where Q0 and Q1 are my input qubits, Q2 is my sum qubit, and Q3 is my carry qubit. Now, in order to get the sum qubit, what I do is first I XOR my Q0 qubit and Q2 qubit and store that result into Q2. After that, I take that result and XOR it with Q1 and store it back into Q2. Then I finally measure that qubit to get the result or the sum part of the half adder. To get the carry part, it's something very simple. We do something very similar to the AND gate in the classical half adder. So we just take these values of Q0 and Q1, use our AND operation, which is actually a Toffoli gate. I'll just get to that shortly. And then we just measure that for the result. So the XOR operation in the quantum circuit is implemented by using the CNOT gate, and the AND operation is implemented by something known as a CCNOT gate. So the CNOT gate is a control NOT gate. So basically what it does is it takes in two bits, right? The bit 1 and bit 2. If the bit 1 is a set bit, that means if the bit 1's value is 1, it flips the value of the second bit. If it is 0, it does nothing to the second bit. For example, if these were the two states of my qubit passed the CNOT gate, 0 and 0, the result I would get is 0, 0. But if I had something like 1, 0, you see 1 is the control bit right here. So my second bit also gets flipped, 1, 1. And if it's 0 and 1, it does nothing. And if it's 1 and 1, what happens is the 0, 0 state, right? Now, if you look at this, this looks very similar to my XOR gate, where your last column is giving the output of the XOR gate. So for example, 0, 0, 0 XOR 0 will give me 0, 1 XOR 0 will give me 1, 0 XOR 1 will give me 1, and 1 XOR 1 will give me 0. Right? So that's how that works. Now, the Toffoli gate, which is used to implement the AND function, is very similar. Very simple. So if I have, it works on 3 qubits, right? So 0, 0, and remember, when we're initializing the Q3 qubit, it's always going to initialize to state 0. So Q3 will always be 0. So 1, 0, 0, and 1, 1, 0, right? Now, what control NOT is very simple. If both the qubits are controlled, are set bits, it flips the last bit, or else it does nothing. So for the first example, both the first two qubits are not set bits, so it does nothing to the last bit. So here again, both the qubits are not set bits. Here, which is very similar, both the qubits are not set bits. And here, because both the qubits are set bits, it flips the last gate. So now if you see, it is the last column is the result of an AND gate. So 0 and 0 will give me 0, 0 and 1 will give me 0, 1 and 0 will give me 0, but 1 and 1 will give me 1. So this is what a CCNOT gate does. Now let's just get to the fun part, the coding part. So namespace half adder, right? And let me give a main function entry point and operation main, right? And I don't expect this main function to return anything, so this will be unit type, right? And now I need 4 qubits, right? For my 4 qubits in the quantum half adder. So use a comma b comma c comma s is equal to, so just qubit, 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 and qubit, right? So with that done, now what I do is I'll quickly go and also create my half adder operation. So operation half adder. So this will basically accept 4 bits, 4 qubits, qubit, which is very similar to what I just initialized down there. So qubit. And this will also not return anything. So that's just a unit return type. So let me just maximize this for better readability, right? And now what I do is I implement my sum operation, right? So the sum basically is just a CNOT gate. First, I take my A input bit and XOR it with my sum and store it back into the sum. So this is my control, and this is my both my target and my other bit, which the control actually shifts if the control bit is set. So then what I do is CNOT B comma S. So after these two XOR operations, we have the result of the sum inside the S bit, S qubit. Now the carry operation is something very simple. So just CC0 A comma B comma C. Perfect. Now we have all that down. So let me just message here. So dollar. So the value of A is, I'll just measure A and put it out there. Message. So remember, every qubit is initialized to the 0 state. So we have B. Right? And then let me call the half adder function with A comma B comma C comma S. Right? And let me also print the values after addition. So this will be my C and this will be my S. So this is basically my carry and this is my sum. Now before we end, we have to reset all these bits. So reset all A comma B comma C comma S. Perfect. Now let's just run this and see the result. So I'm just going to open up the result. So as you can see, I have A value as 0, B value as 0. So my carry is 0 and my sum is 0. Now what I'll do is I'll change the value of A to 1 by using what we learned from the single qubit video using the poly X gate. So now let's run this again. So here we have our result. A is equal to 1, B is 0. So 1 plus 0, the carry will be 0, but the sum will be 1. Now let's go to another input, X of B. Right now, both A and B are 1. So we should get our carry as 1 and our sum as 0. And that's exactly what you see here. A is 1, B is 1. So our carry is 1 and our sum is 0. So that is how you implement a quantum half adder. So thank you for watching this video and keep working on your quantum programming skills. See you very soon or with the next video in the playlist.